So welcome back to online lecture series on design of machine elements. This is our last lecture on pressure vessels. In our previous lecture we have discussed about the compound cylindrical shells and the stresses which are generated in the cylindrical shells. So we will continue from that only. We have discussed about the inner cylinder and outer cylinder of the compound cylindrical shell. We have obtained the values of tangential stress and radial stress for the inner cylinder and the outer cylinder. So here the first equation here, let us give this some name, equation 1, okay, and this is equation 2. Now the equation 1 is the tangential stress at the inner surface of the inner cylinder. So if we go to the inner cylinder, then this value, this is the value AB. AB is obtained by equation number 1. Okay, this AB in the inner cylinder is obtained using equation number 1, which we have already derived. And the radial stress is 0. Now we will move forward and obtain maybe I am not able to write this down for some reasons. So let me use the regular pencil here. So we will now calculate the tangential stress at the outer surface of inner cylinder. Okay, so now we will calculate this part. So again we will be utilizing the equation A and B, which are written over here. So let's copy them once again. So now what we will do, in this case we will put PO as P, RO as R2, RI as R1, and X as R2, because now we are discussing about the outer surface of inner cylinder. So what will be the value of sigma T? Let's see. So what we will get here is equal to minus p upon r2 square minus r1 square into r2 square plus r1 square. So this is I forgot to give different names here. Okay, I have given it sigma t1 and sigma r1. Here this will be sigma t2, sigma t2. So this will be our third equation, and if you check the value of sigma r2, that is the radial stress at the outer surface of the inner cylinder. So here it will be minus p r2 square divided by r2 square upon minus r1 square into 1 minus r1 square upon r2 square. So if we try to find out the answer, then the final answer will be minus p. So let me write down over here, sigma r2 will be equal to minus p. You can check it by yourself, it is quite straightforward. So what we have obtained here, equation number 4. Now if you see this sigma t2 in this figure, the sigma t2 is given by this value CD. So CD is given by equation number 3. Okay, so this equation 3 is given by CD in the previous figure over here. Okay, now we will focus on the outer cylinder, that is this one. Let's copy this again at some other location. Maybe this will be the right place. First of all, let me copy the important portion. In our slides. And we will also require these two equations C and D for our derivation. So let's bring them over here. Now we will calculate the tangential stress at the inner surface of the outer cylinder. Okay, so for that what we can do is we can put for this figure. Now see, the things will change. Pi will be equal to P, Rho is equal to R3, Ri is equal to R2, and as far as x is concerned, x will be equal to R2 in our case, because we need to calculate for the inner surface. So now we will calculate the value of sigma T3, which is equal to P into R2 square divided by R3 square minus R2 square into 1 plus R3 square divided by R2 square. So what we will obtain here, P into R2 square into R3 square plus R2 square divided by R3 square minus R2 square. So this is sigma T3. This will be let me see, the equation number that we need to give over here is equation number 5. This will be equation number 5, and as this is positive value, this will be the tensile stress. See, in case of the previous equations, this was compressive because of negative value. Okay, and here also this value was also compressive. And this sigma T3 in this figure is denoted as this CE portion. So this CE is denoted by equation number 5, which we have already derived. Now similarly we can calculate the radial stress. Radial stress at the inner surface of the outer cylinder. So now we will utilize the equation number D over here. So sigma R3 is equal to P into R2 square divided by R3 square minus R2 square into 1 minus R3 square divided by R2 square. So if you calculate carefully, then this answer will arrive as sigma R3 is equal to minus P. You can check it by yourself. So this will be the equation number 6. Let me first copy this portion in our main slides. Okay. So we will save this. Now let's move forward. Again, we will be using these equations over here. So what we will calculate now? We will calculate tangential stress at the outer surface of the outer cylinder. So to achieve this, we need to change the terminology of equation C and D. So here, instead of Pi is equal to P, Ri is equal to R2, Ro is equal to R3, and instead of X we can put R3. So sigma T4, this will be known as sigma T4 is equal to P into, instead of Ri we can put R2 square divided by R3 square minus R2 square into 1 plus R3 square divided by R3 square. So if we further simplify this, then here the answer will be 2P R2 square R3 square divided by R3 square minus R2 square. This is sigma T4. Now which number we will be giving? We will be giving equation number 7. Similarly, we can calculate radial stress at the outer surface of the outer cylinder. So again we will be using the same terminology and apply it onto the equation number D. So sigma R4 equal to P into R2 square divided by R3 square minus R2 square into 1 minus R3 square divided by R3 square. So this will be sigma R4 equal to 0. This will be our equation number 8. And one thing I still need to mention, that this sigma T4 that we have obtained in equation number 7 is nothing but GF value, that is this value is obtained from the equation number 7. Now let's copy this portion. Here. Okay, so we have calculated all the stresses in this whole whiteboard. So this is the end of this chapter over here. There might be few small topics which could be left out by myself only. So in case if you find such kind of topics, that you can do it by your self study also, because the main theories I have covered here. Maybe some small definitions that are missed out, so you can do it by yourself. So now what we will do here is we will go through the quick revision that what exactly we have studied in this entire chapter. So these are the topics that we have covered. First we begin with the introduction, that the pressure vessels are used for storage of fluid under pressure, and this fluid can undergo change of state or may combine with some reagents in the chemical plant. Now these pressure vessels have to be designed with extreme care, because if it gets failed, then it can end up in an explosion which may cause loss of life and property. So material can be brittle such as cast iron, or ductile such as mild steel. Then we went through the classification of pressure vessel. First is thin, according to the dimensions, which is thin shell and thick shell. If the wall thickness is less than 1/10 of the diameter, then it is thin, and if it is more than 1/10 of diameter, then it is thick shell. Then according to the end constructions also, we discussed that it can be open end or it can be closed end. Then we discussed about the types of stresses that can be generated in a thin cylindrical shell due to an internal pressure. So there are few assumptions that we made. Two kinds of stresses which can be generated. First is the circumferential or hoop stress, which occurs circumferentially, and the longitudinal stress, which occurs in the transverse direction. Then one by one we took both the cases. First we derived the equation for the circumferential or hoop stress, or we can obtain the thickness of the thin cylinder based on this stress. Then we discussed about the longitudinal stress, in which circumferential longitudinally there are two parts in which this shell can break. And these are the final equations of longitudinal stress and the thickness based on the stress. Then the next is spherical shells, that is thin spherical shells subjected to an internal pressure. So here also we obtained two parameters for the design. First is the diameter and second is the thickness. So we obtained the diameter and the thickness. Then we moved over to thick cylindrical shells subjected to an internal pressure. So here this is the figure of thick cylindrical shell, in which we discussed about the tangential stress distribution and radial stress distribution. We took a small infinitesimal strip having thickness dx and located at the distance of x from the center of the shell. And then these are the nomenclatures, and we first introduced the Lamb's equation for the tangential stress and the radial stress. Let me change this somewhat so that it is easy to understand. I think now it is properly visible. There it is. So sigma T and sigma R. Then here you can see that we have derived the maximum value of this tangential stress and minimum value of this tangential stress. After that, we also calculated the maximum and minimum value of radial stress based on the Lamb's equation. Now we took two different cases. First is for the brittle material, we obtained the thickness A, which is based on the maximum normal stress theory, and then we applied the same theory for the ductile material based on the maximum shear stress theory. We obtained the value of thickness for both the kind of materials. So these are the final equations that we have obtained. Then we studied about Bernoulli's equation, which we directly need to accept this. We don't have derivation for this in the syllabus. And then we have Claverino's equation. Then we discussed that why compound cylindrical shells are required, because if the value of this pressure, internal pressure, is higher than the allowed stress, then there can be no thickness which can prevent this kind of failure. So for that we introduced the compound cylindrical shell, and apart from that there is also a theory of plasticity as well. Then these are the stresses in the compound cylindrical shell that we discussed in detail. So first of all, we modified the Lamb's equation for the inner cylinder, which only experiences the external pressure, and the same thing we followed for the outer cylinder, which only experiences the internal pressure. Then one by one we obtained the tangential and radial stresses at the inner and outer surface of inner cylinder. So it contained total 4 equations, and similarly we calculated the tangential and radial stress at the inner and outer surface of the outer cylinder. So in total we obtained 8 different equations for the stresses which are generated in the compound cylindrical shell. So that was the end of this chapter, pressure vessels. And as I told you that if you find that some small topics are left out in this lecture series, then definitely you can prepare it by yourself, or if you don't feel comfortable while learning it by yourself, then you can put it in the comment section. I will be happy to add those lectures as per your requirements. So this is the end of the lecture series for pressure vessels in the subject of design of machine elements. Thank you so much for watching this video.